Hello everyone. So today we are going to talk about today we are going to study Module 1, Lecture 5, which is about momentum. But before we start, let me recap what you studied last time. So the first thing that you studied last time is dot product, which is a transformation of two vectors into one scalar. So suppose that you have vector A and vector B like this. The two vectors make an angle theta. A dot B is defined to be the magnitude of A multiplied by the magnitude of B multiplied by cosine theta, where theta is the angle between the two vectors. Now in terms of components, A dot B is equals to AX BX plus AY BY plus AZ BZ, where A is equals to AXI plus AYJ plus AZK, and B is equals to BXI plus BYJ plus BZK. Okay, so you can see that A dot B is equals to the sum of the product between the same component X and X, Y and Y, Z and Z. Okay. Next, we talk about work, which is a scalar quantity that measure how a force affect the motion of the object. By affect here, I mean how the force make the system move. So if you have a force that does not make the system move, then the work is zero. Okay, and if the force make the object move in the same direction as the force, then the force is positive. Or if you have a force this acting in the opposite direction to the motion of the system, then the work done by that force would be negative. Okay, and work from point x1 to point x2 is defined as the integral from x1 to x2 of f dot dx. So this dot is the dot product that we just talked about in the last page. Okay. In terms of a picture of how force is related to the real situation. So if suppose you have a box here, and you put the box by this force that make an angle theta with the horizontal axis. So the question is, what is the work done by this force? So you can see, because the box is moving in this direction, so this is the displacement of the box. From the equation f dot dx, this just means that you need to calculate the force by choosing the component of the force that's pointing in the same direction as the displacement, which in this case is f cosine theta. Then you multiply it by the small displacement dx, and then you do the integral to sum over all the multiplication f and dx along the whole displacement, okay, from x1 to x2. Now, we also talked about kinetic energy last time. Kinetic energy, denoted by EK, is defined as equals to 1/2 of mv squared, where m is the mass and v is the speed of the system. Now, the concept of work and kinetic energy is linked together by this work energy theorem, which says that the work done by the total force is equal to the change of kinetic energy. So when we say the work done by total force, it means you need to calculate the whole force, the summation of all the forces is acting on the system, and you calculate the work that is done by that force, and then it must be equal to the change of the kinetic energy. Okay, work total equals to EK2 minus EK1 always. Then we talk about conservative force. So conservative force is a type of force that produces work that depends only on the starting and the end points of the motion and not the path. So in order to explain this, let me try to explain by saying what is not a conservative force. Okay, so what is not a conservative force? For example, friction is not conservative force. Friction is not a conservative force. Why? Because if you think about the work done by friction, it does depend on the path. Okay, so for example, if this is a room, okay, with a room with rough floor, okay, and if you want to move a box on this floor from point A to point B, of course, because you have friction on the floor, the work done by friction, if you move the box along this path, let's call it path 1, and along this path, we call path 2, and along this path, which we call path 3, normally will not be equal. Okay, so the work done by friction from A to B using path 1 would not be equal to the work done by friction from A to B along path 2, and is not equal to work done by friction from A to B along path 3. Okay, so this means that the work done by friction does depend on the path and not just the starting and the end point. So friction is not conservative force. So what kind of force are conservative force? The kind of force that produce work that depends only on the starting and the end point. Those kind of forces, for example, gravity, spring, and electrostatic. These are the three main kinds of force that give you that are conservative forces. Next, we are going to talk about potential energy. So what is potential energy? A potential energy has relation to work done by conservative force. So work done by conservative force is defined as the negative change of potential energy, W from 1 to 2. The work done from point 1 to point 2 by conserved force must be equal to minus of the change between potential energy of point 2 and potential energy of point 1. So if you compare this to the previous relationship that we know, the work kinetic energy theorem says that the work done by total force is equal to the change of the kinetic energy. Okay, so if you compare between them, this one says that the work done by the total force is related to the change in the kinetic energy. But this one says that the work done by conservative force is related to the change in the potential energy. Okay, so they are similar, but they are different. Now, if you combine the two of them together, you get something called conservation of energy. So basically, conservation of energy says that if the work done by the total force is equal to the work done by conservative force, if that is the case, then the change in the kinetic energy here must be equal to the negative change in the potential energy here. And that means what we have finally is that delta EK must be equal to delta EP. Okay, actually it should be minus, equals to minus delta EP. And so that means EK2 plus EP2 must be equal to EK1 plus EP1. Okay, and that means the total energy at point 2 is equal to the total energy at point 1. Okay, because total energy is defined as the sum between kinetic energy and potential energy. Okay, so just to summarize this again, whenever the work done by the total force is equals to the work done by conservative force, we will have conservation of energy. But if the work done by the total force is not equals to the work done by the conservative force, then the conservation of energy is not true for that kind of system. Alright. We also talked about power last time. So power is the rate of change of the work. So P is equals to dW by dt. And because W is equals to, actually this has to be integral. Yeah. So P is equals to d by dt of integral of f dot dx. Okay. Now, if force is constant, this means this f is constant, then you can put f out of the integral, and what you have is just dx by dt here. So P equals to f dot dx by dt, or f dot v. This is only true when the force is constant. Okay, so this is how you find the power. And then we talk about efficiency. So efficiency E is defined as the output over input multiplied by 100. What is this output and input? So it could be work, it could be different in energy, or it could be power. Doesn't matter. Okay, it could be for example, power. It could be energy, or it could be work. Whatever. As long as you put you choose the same thing as the output and the input. So for example, if you choose power, this would be power output and power input. If you choose energy, this would be energy output and energy input, something like this, and you get the same value of efficiency. Okay, and so that's it for the recap from lecture 4. Now we start lecture 5, system of particles and momentum. First of all, what is the system of particles? So system of particles is just like the name suggests. It is a system that is composing of a lot of particles. And actually, a lot of system in nature is a system of particles. So for example, if you look at this glass of water, normally in the past that we have studied, we think of this whole thing as a single mass without anything smaller inside. And we think of the whole thing moving together, right? But if you zoom in, if you look into more details, you see that in this chunk of water, there are a lot of smaller molecules, which each of them has their own mass, and each of them is moving with their own velocity, and all of them are moving randomly relative to each other. So in order to understand how everything moves in more details, you need to look into how these smaller parts are moving. Okay, but also try to look at how all these parts are moving is so complicated. So that is why at the beginning, what we are going to do is to try to see the average of the motion of this whole thing. Okay, and that is why we need the concept of average position, velocity, acceleration. So I mean average position, average velocity, and average acceleration, etc. Okay, and that leads us to the concept of the center of mass, which is the representation of the whole particles. So if you look at this picture, there are a lot of particles in here. But if you think of this whole thing as a system, we want a means to describe the average motion of all the particles here. And that is the concept of the center of mass. So center of mass is, imagine that it is as if you have a point here. Let's use this black dot, okay? So it is as if every particle here are concentrated within this black dot. And in order to describe the motion of this whole thing, we are going to say that the average position is the position of this black dot, and the average velocity is the velocity of this black dot, which we call velocity of the center of mass, and also the acceleration of the whole thing, the average of them, is the same as the acceleration of this black dot. Okay, so again, this black dot is the representation of the whole thing. And so we will use the notation RCM to represent the average position or the position of the center of mass of the whole particle in the system. VCM is the notation for the average velocity or the velocity of the center of mass, and ACM is the average acceleration or the acceleration of the center of mass. Okay. Now, the next question surely is, how can we find RCM, VCM, and ACM, which is the average of the whole thing? So in order to find RCM, for example, R is a vector, this a position vector which points in 3 dimensions x, y, and z. But for simplicity here, let us consider only in the x direction. What is the average x position of the whole thing? How can we find that? In order to find, we start with xcm equals to summation of the product between the mass of the nth particle multiplied by the position of the nth particle xn, okay, and then divided by the whole mass big M. So big M here is defined as the sum of the smaller n. So suppose that your system is composing of smaller n part of system, then summing all the parts together, you have the total mass. Okay, and this formula is the formula to find the average x, the average position in the x direction of your system, or the position of the xcm. Okay, if you can find xcm, then you can of course find vcm and acm by doing the derivative with respect to time, just like this, or in terms of summation it will look like this. Okay, now let's see an example of how to find xcm and also actually ycm. So suppose that your system is composing of just 2 particles, the blue one and the red one. The blue one has mass of 2, well, you might put it as 2 kilogram, and is 20 kilogram, and they are situated at different points in x and y. So the blue one is at minus 3x and 10y. Okay, so the mass m2 is at 4 in the y direction and 10 in the x direction. Now, how are you going to find the center of mass of this system composing of the blue one and the red one? Okay, let us first starting by finding xcm, the center of mass position in x direction. Just like the formula suggests, so let me try to rewrite it again over the whole mass. So that would be, let me start by mass, the blue mass. Okay, so blue mass has mass 2, and then the position in the x direction is minus 3 plus mass 20, and the position in the x direction is 10 over the total mass, which in this case is 2 plus 20. Okay, sorry. So what you have is 194 over 22, right, meter. Okay, so if the unit of I leave the unit to be arbitrary. So here the position of the center of mass in the x direction of this system between this composing of these two mass is at x equals to 194 over 22. So that is something around this point. Okay, something around this point. 194 over 22. All right. Now the next thing is, what is the position of ycm? We need both xcm and ycm in order to find where the actual position of the average is Okay, so YCM can be calculated similarly. Mn Yn over the whole mass. Okay, so that would be 2, the mass of the blue one, 2 multiplied by 10 plus 20 multiplied with 4 over the whole mass, which is 22. Okay, so that is going to be 100 actually, right? 20 but plus 80, yes, over 22. So that is the position of YCM, and that would be somewhere around here. Okay, so suppose that is 100 over 22, which is 5, well, nearly 5, 4 something. Okay, so you can see that this is the position of XCM and YCM, which is the position of the center of mass. Okay, so this is the representative of these two mass together. You have this mass, you have this mass, and you combine them into just one mass of 22 kilogram, and it is situated here at the position XCM and YCM. Okay, so that is how you find the center of mass position. And if you know the center of mass position, to find the center of mass velocity or the center of mass acceleration, you do something similarly. Alright, so and that leads to our first homework. So this homework says that 4 masses are located at the corners of a rectangle as is shown in the figure. The origin is chosen to be at the center of the rectangle here. Okay, determine the position of the center of mass of the system. Alright, so you see this is the origin. So this mass is at y equals to 3, right? Because this whole thing, the difference between this whole thing is 6 meters, and because the origin is at the center, so here is just 3 meters, and as well as down here 3 meters, and you can see that this whole thing has the distance 4 meters apart. So that means here this is just 2 meters basically. Alright, so now that you have this information, you should be able to calculate the position of the center of mass. Okay, that is your homework. Right. Okay, so next let us look at this example. 2 particles are moving with velocity as shown in the diagram. Determine the velocity of the center of mass. Okay, so here what you need to find is the velocity. So we start with the formula for the velocity. Okay, so similarly to when we talk about the position of the center of mass, when we talk about the velocity, we can also talk about the velocity in the x direction and the velocity in the y direction. So I just write down separately here. The velocity of the center of mass in the x direction is equal to summation n of mn vn in the x direction divided by the whole mass. So what we have here is 0.4 kilogram multiplied by 3 plus, well, if you look at this mass, there's no component of the velocity in the x direction, so you plus 0, right, over the whole mass, which is 0.4 plus 0.6. Okay, so that is VCMX. All right, let me move this a bit down further. So here what you have is 1.2 over 1, which is basically just 1.2. That is the velocity of, well, with the unit meter per second. Okay, that is the center of mass velocity in the x direction. Now the center of mass velocity in the y direction can be computed similarly. Sum of n, mn, vn, but y. Okay, so that would be equals to, of course, this one has no component of velocity in the y direction, but this one has. So what you have here is just 0 plus 0.6 multiplied by 2 divided by the whole thing, which is still 0.4 plus 0.6. So what you have here is just 1.2 meter per second again. Okay, so you can see that the component of the center of mass velocity, or the average velocity in the x direction, is just 1.2 meter per second, and that is coincidentally equal to the velocity of the cm in the y direction, which is also 1.2 meter per second. Alright, now the question asks you to find the velocity of the center of mass, so you might just answer this, or you might say that v as a vector, vcm is equal to 1.2 I plus 1.2 j, okay, meter per second. Again, this I and j are unit vectors that says that this 1.2 is pointing in the x direction and this 1.2 is pointing in the y direction. Alright. Next, let us talk about how to find the position of the center of mass and the velocity and acceleration as well when the system is not composing of smaller chunks of particles or smaller discrete mass, something like that. But what if the system is composing of a continuous piece of mass? Then how can you find xcm, vcm, and acm? When I say continuous piece of mass, what I mean is this. For example, if you have a uniform rod with length L and it is lying on the x-axis, you can see that in this case, this rod is composing a lot of mass, of a lot of mass, but it is not like a discrete pieces of mass, it is a continuous piece of mass. Now, how can you find the position of the center of mass of this rod? In this case, because the mass is continuous, instead of using summation, instead of using sigma, you need to use integral. Okay, so you can see that the difference in the notation is just in the numerator here. So instead of just summation, you use integral now. Integral of x dm, integral of v dm, integral of a dm. Okay, divided by the whole mass. Now, let us see how to use this in action by trying to work out this example. This example asks you to find the center of mass of this rod is at the middle of the rod. Okay, so how to do it? Because this rod is in x direction, so xcm in this case must be equal to integral of x dm over the whole mass. Okay, so in order to do this integral, you need to change the variable, either change x to m or change m to x, because if not, you cannot do the integral, right? Because m and x are two different variables here. And in order to change m to x, so in this case we choose to change dm to dx, we need to introduce a new notation which we will call lambda here. Okay, so this lambda is defined as the total mass divided by the total length. In other words, this lambda is what we call linear mass density. Okay, it is mass divided by the length. You might have heard of the word density before. So density, normally we talk about mass divided by the volume. That is the volumic mass density. Okay, in this case it is just the mass divided by the length. So that is what we call linear mass density. How much mass it is, how much mass there is in 1 unit length of the rod. Okay, and in this case this lambda, or the linear mass density, is a constant. So dm, the small mass dm, must be equal to the density lambda multiplied by the small length of the mass dx. Okay, this is a very important concept. We use this again and again for the whole course in your first year at least. dm, the small mass of this piece dx, is equal to lambda dx. Okay, one more time. What I mean is, if you consider this piece, this small piece of the rod which has length dx, and you ask what is the mass of this small piece of the rod dx, you can find that this small piece of the rod dx has the mass dm, and that dm must be equal to the density lambda multiplied with dx, the small piece, the small length of the rod dx. Okay, and now because of that we can change this dm into lambda dx, and we will have integral x and then lambda dx from, of course, from 0 to L, because you want to do the integral from this point which has x equals to 0 to this point which is x equals to L. Okay, x equals to 0 to x equals to L. Okay, and divided by m. Now because lambda is a constant, what you have from here is just lambda integral from 0 to L of x dx over big M. So what you have is lambda x squared over 2 from 0 to L over M. And so what you have is lambda L squared over 2m. Okay, that is the position in the x direction of this rod. But the question asks you to show that this xcm is actually at the middle of the rod. So the middle of the rod is actually just the position L over 2, right? Because the whole rod has length L. So in this case, you can just change this a little bit more. You know that lambda L, let me write here. Because lambda is equals to m over L, so lambda L is equals to m. Alright, so here you can rewrite everything as L multiplied by m divided by 2m, and that is L over 2, just like what the question asked you to prove. Okay, so this m comes from lambda and 1L, because this is L squared. Okay, lambda L is m, so that you have L over 2. Okay, the next question tells you that a circular sheet of radius r has its center placed at 0, 0. A circular hole with radius r over 2 is made. So you previously has the whole circular sheet, and then you cut out this hole as is shown in the diagram. Find the position of this new center of mass. Okay, so the situation is, first at the beginning you have the whole thing, then you cut, you have the So the situation is like this. At the beginning, you have a complete blue circle. Then you cut out this hole, white hole. Okay, and you are asked what is the new position of the center of mass. Alright, so this might look difficult, but it is not actually. The trick to do it is like this. Let me try to draw x and y axis again, and let me use different dot to represent different object. So this blue dot represent the center of mass of the total. Okay, I make a note here. This blue dot here means the cm of the total of the complete circle when the hole is not made yet. And then I'll use this black one for the center of mass of the hole. Okay, what does it mean, the center of mass of the hole? It means that because you cut out this hole by removing this part of the circle, right? So what I mean is, if you put this small circle back into this big circle, you get the complete circle. Okay, so when I say the center of mass of the hole, it just means the center of mass of this small circle that is cut out. Okay, so it used to be here, right? The center of mass of the small circle used to be here, and the center of mass of the complete big circle was here. Okay, now you have another center of mass, which is the center of mass of the circle with the hole, which is what the question asked you to find. So let me denote that center of mass by the red dot here. Okay, so the red dot here is the center of mass of the circle of the big circle with the hole. Okay, so now you can see that there are three center of masses here. So the relationship between this center of mass is like this, because this is in the y direction, so I just use y cm is equals to the black y cm. Hang on. Okay, before we get to that point, let me put it this way. So we know that normally, so this is the formula. Okay, normally we know that ycm is equals to, for example, m1 y1 plus m2 y2 over m1 plus m2, right? This is the formula. Okay, so in this case, we use this formula to to find where the red dot is by doing it this way. We will say that each one of these has different mass. So the blue one has the total mass. The black one, let's say it has mass m1, and the red one, let's say it has mass m2. Okay, so and we will put all of this in the formula. ycm, which is the center of mass position of the blue one, must be equals to m1 plus y1. Here y1 is the position of the center of mass of m1, and then plus m2 y2, where this y2 is the position of the center of mass of m2, and it is what we would like to find. Okay, and then divided by the whole thing. Now this whole thing is the total mass, which is the mass of the blue one, of course, so that would be big M. Okay, now you put everything from the question to the formula. You see that this YCM must be 0 because the center of mass of the blue one is at the origin, so Y must be equal to 0 there. So you have 0 here. Okay, then because you move this M up here, this M multiplied with 0 give you 0, so what you have left there is just okay, you have M1. Now what is Y1? What is the length, the displacement or the distance here? What is Y1? You can look for it from the picture. This is just minus r over 2, okay, because it is going down, so it is minus r over 2. Minus r over 2, and then plus m2 y2. Okay, so now if you know what m1 and m2 is, you can find what is y2. Okay, so what we are going to do next is to find what is m1 and what is m2. Okay, let me try to show that here. How can we find m1 and m2? We will need to use that trick again that we used in the last question, which is the concept of density. Okay, density is defined as mass over something. In this case, because this is a two-dimensional object, right? A two-dimensional object. So instead of define density as mass over volume, we will define something called area density, which will use the notation sigma. Okay, it looks like number 6, similar to a number 6, but the tail is drawn horizontally. Okay, sigma, we call this guy sigma or area density, and we define as the total mass divided by the total area. Okay, so that means okay, so we define this area density. Now we are ready to find what m1 and m2 is. Okay, so m1 must be equal to sigma multiply with the area of multiply with area 1, which in this case is equal to pi r over 2 square. Okay, so we know that m1 must be equal to pi sigma r over 2 r square over 4. Okay, that is m1. Now what is m2? m2 must be equal to the total mass minus m1, right? So the total mass is equal to sigma multiplied by this whole area which is equals to pi r square, right? Because the radius of this big blue circle is r. So this big M is just sigma pi r square. Now we subtract that with the small m1, which is just sigma pi r square over 4. So that means m2 is equals to sigma pi r square multiplied by 3 over 4. Alright, now we put all of this back into the equation, and what we have, so let me put it in here. What we have is m1 r over 2 equals to m2 y2. Now we put m1 and m2 into the equation. What we have is pi sigma r square over 4 multiplied by r over 2 must be equals to 3 pi sigma r square over 4 and then y2. Okay, now you can cancel pi, you can cancel sigma, you can cancel r square, you can cancel 4. Okay, so right, so now you can see that finally what we have is y2 must be equals to r over 6. Okay, so that means here this is r over 6, and that is the position of the center of mass of this circle with the hole. Okay, so in other words, the center of mass that we're seeking is this one, and it is at the position r over 6 above the origin. Okay, so this is how you do it. If this is unclear, please feel free to ask your lecturer or me or the TA later. The next concept that I would like to talk about is the internal and external forces. What does that mean? So when you define a system, you simultaneously define what is not the system, right? So for example, if you look at this picture, your system is composing of this red mass and this blue mass. All right, so and what is outside is not part of the system. So let me draw it this way. Sorry. The thing that is in this green frame is what you call the system. Okay, and what is outside is the environment, or well, whatever you call it. Okay, now when you talk about internal force and external force, what it means is if you have the force that is acting on the system and that force is within the system, you call that internal force. But if you have a force that's acting from outside of the system, then you call that external force. So in this case, an example of an internal force is the spring force. Okay, the spring force. This is internal force because the spring itself is within the system. And what is the external force? It's gravity. Why? Because gravity is originated from the earth, which is not part of the system. So in this case, gravity is the external force. So I hope that is clear what internal and external forces are. So next, we talk about Newton's laws on system of particles. So previously we talked about Newton's law that is applying to only single particle system. Okay. Now, if your system is composing of more than one particles, how will Newton's law says about that system? So we start with Newton's first law. Newton's first law says that the momentum of the center of mass is constant relative to an inertial frame of reference as long as the total force acting on the whole system is vanishing. So what this means is when your system is composing of many particles, the force is acting on the total force is acting on the particle is the force that is acting on every particle in the system. Now, when the force acting on every particle on the system, each particle may have different acceleration, but if the total forces are zero, the total momentum, well, actually I should not say the momentum of the CM here, sorry about that. It should be the total momentum. Okay, so sorry about that. So the total momentum, which means if you add momentum of every particle in the system together, then you get the total momentum. If the total force is acting on the system is equal to zero, then the total force, the total momentum will be constant. Okay. But again, what is important here is that each component of the system may still move with non-constant momentum. Alright. But the average or the total momentum, sorry, not the average, but the total momentum would still be constant. And then the second law says that the total force this acting on the system doesn't matter which particle it is acting on. You sum over, you treat the whole thing as the system. You sum every force is acting on the system, and you discover that it is equal to the mass of the total system multiplied by the acceleration of the center of mass. Okay, the mass of the total system multiplied by the center of mass. Again, that doesn't mean that each component of the system will have the same acceleration. Each component or each particle within the system may still have different acceleration, but if you sum them over, find the average acceleration, what you will find is that the acceleration of the center of mass, which is the representation of the whole system, would have this relationship. The total force is equal to the total mass multiplied by the acceleration of the center of mass. Okay. Now, as an example, think about this. If you have a stick, let's say, a stick on a floor, okay, then you kick the stick on this side with a force F, and if this is the center of mass of the stick, what happens is that later on the stick will start to rotate. We start to move away and rotate with the acceleration of the CM being ACM. Okay, and this guy will have its own acceleration, this guy will have its own acceleration. Okay, so this okay, to make it clear, let me change how I write it. So this guy will have yes, different acceleration, this guy will have different acceleration, but the center of mass will have acceleration ACM, and this ACM will be equal to F, the force, divided by the mass. Okay, so in this case, I may have spoken wrongly, but this stick has to be put on a frictionless floor. Okay, frictionless floor. So that the total force is just this force. If that is the case, then ACM will be equal to F over M. Okay, now what is the acceleration of this guy and this guy? Of course, this point up here will have more acceleration than ACM, and this point down here will have less acceleration than ACM. Okay, and that is because, well, you can see that they are all starting at this point, and then later on this guy move faster than this guy, and this guy is move faster than this guy. So that means this has the maximum acceleration, this has maximum acceleration ACM, and this has acceleration that is less than ACM. Okay, so you can see now that if you have a system of particles, this stick is composing of a lot of particles. Each point may have different acceleration, but the CM point will have the acceleration ACM, which has this relationship F over m, where m is the total mass of the stick. Okay, now if the third law, Newton's third law applying to system of particles says that the total internal force would be 0. Okay, what does that mean? So if you remember my the previous discussion that we talked about the Buffy and the man that's trying to pull this guy. Okay, we discussed last time that for the Buffy he will see the force pulling from the guy, and for the guy he will see the force pulling back. Okay, these two forces are action and reaction forces. They have equal magnitude but opposite direction, and we say that this thing cannot cancel with that thing. But that is only because when we consider the system, if we consider only the Buffy, then we want to see only the force that's acting on the Buffy, but not the force that the Buffy is acting on something else. And if we consider the man as a system, we will consider only the force that is acting on the man and not the force that the man is acting on something else. Okay, and so that is why these two forces, we say that these two forces are acting on different objects, so they cannot be cancelled out. That is the normal third law. But what if you consider both the man and the Buffy, both of them as a single system? What happens? So if both of them are part of one system, what happens is this is the force. This is a force that's acting on this system. This is a force that's acting on this system. But because both objects are part of the same bigger system, and we treat so in this case, this is the force is acting on the whole system. This is also the force is acting on the same whole system. Okay, so now you can add them up and cancel them out. Okay, so that is the key. It depends on how you define your system. If your system is composing of both the Buffy and the man, in this case, these two forces are acting on the same system, so they can cancel each other out, and that is why Newton's third law applying to this kind of system will say that sigma, the summation of the internal force, would always be 0, because in this case the internal force is always the action and reaction pair, so it will cancel out, of course. Okay, it's just this thing is just a consequence of normal Newton's third law, and that also leads back to this thing that I skipped when I discussed the second law. Okay, you can see here summation of the total force is equal to the summation of the external force. The reason is because the total force is composing of the external force and the internal force, but the total internal force is always 0. So that is why total force is equal to total external force and equals to total mass multiplied by the center of mass acceleration. Okay, and that leads to another important topic in physics, which is conservation of momentum. So we have already defined momentum in our last lecture. It is just the mass multiplied by the velocity of the mass. Okay, just that. Now what it means by P before and P final, what it means here is P before is like, for example, at time t equals to 0. P final is some any other time, maybe t equals to 5 seconds, 10 seconds, whatsoever. Okay, but what we have here is just that conservation of momentum says that as long as the total force that's acting on the system is 0, Okay, as long as the total force is acting on the system is 0, then the total momentum of the system would not change at any time. Okay, this is a consequence of the first and the third law that we just discussed before. Okay, as long as there's no external force acting on the system, the total momentum of the system will conserve. But again, if you look only at the part of the system, you may still see that the momentum of that system might change. For example, if you have two masses here, m1 and m2, okay, if these two has initial velocity v1 and v2 and is moving on a frictionless floor, so in this case, if you treat the red mass and the green mass together as the system, then after they before they collide with each other and after they collide with each other, the total forces acting on them, on this one and this one together, would be 0. Okay, so the total momentum of this system plus that system would be 0. Now, what if you treat only the red mass as the system but not the green mass? If you look only at the red mass, in this case, when it collides with m2, there would be a force from m2 acting on m1. Okay, so in this case, the external force, this becomes an external force to this system. So the momentum of m1 before and after collision will not be conserved. Or if you look at m2, when m1 collides with m2, there would be some force from m1 acting on m2. And in this case, the total force that's acting on m2 is not 0, so the total momentum of m2 is not constant. Only when you combine the two together, that the force that m2 acting on m1 and the force that m1 is acting on m2 will be cancelled out, and the total momentum would be constant. Okay. Now let's move on to the next example. What happens if you have some external force? Okay, so let's consider this case. Again, you have red mass, green mass with initial velocity v1 and v2. But now you have the floor as well, where the floor is rough and there's friction on the floor. So in this case, if you treat only m1 and m2 as the system, the external force here is the friction. Okay, because friction is caused by the floor, which is not part of the system. And because there's friction, this is external force, so the total momentum of m1 and m2 will not be constant. Alright. Now, you might ask, what if you treat the floor as part of the system too? So in this case, your system is composing of 3 objects, m1, m2, and the floor. Of course, if you do it this way, then friction would become the internal forces. And now, the whole thing, including the floor, will have constant momentum. Okay. But, well, we do not normally think of the floor as the part of the system in a normal circumstance, but if you want, you may. Okay. Okay, so that is about the conservation of momentum. Let's talk about collision. Okay, we used collision as an example of conservation of momentum before. So now we will analyze this case in more details. There are 2 kinds of collisions that we are going to talk about normally. This elastic collision and inelastic collision. What are the difference between the two? For elastic collision, the total energy is conserved, but for inelastic collision, the total energy is not conserved. Okay, that is the only difference. But in both cases, the total momentum would be conserved. Okay, so for elastic collision, energy is also conserved, the total one. For inelastic collision, only the momentum is conserved, but the total energy is not. Okay, so next, we are going to talk about elastic collision. So what is elastic collision? So if you look at this picture, this is mass m1, m2 with initial velocity u1, u2, and after the collision, the mass m1 changed its velocity to v1, and mass m2, change its velocity to v2. Okay. You can prove from conservation of energy and conservation of momentum that u1 plus v1 must be equal to u2 plus v2. In this case, the energy that is involved in this kind of system is only kinetic energy. So in order to, it is very easy to prove this. Let's see. First of all, we write down the conservation of momentum. You will have m1 u1 plus m2 u2, and that must and that must be equal to m1 v1 plus m2 v2. Okay, so that is the first equation. Then the second equation is the equation of kinetic energy, because in this case you have only kinetic energy, and you have 1/2 of m1 u1 square plus 1/2 of m2 u2 square equals to 1/2 of m1 v1 square plus 1/2 of m2 v2 square. Okay, so that is the second equation. Now from these two equations, if you rearrange equation 2 a little bit, you see that you have, so first of all you multiply the whole equation 2 by 2, so you get rid of all the 1/2 here. Okay, and then you rearrange equation 2 a little bit. What you have is m1 u1 square minus v1 square equals to m2 v2 square minus u2 square. Okay, so let's call this equation 3. And for equation 1, from equation 1 you rearrange it a little bit. What you have also, okay, so let me take it. Okay, so here this is from equation 2. Okay, now I would like to rearrange equation 1. So from equation 1 you have m1 u1 minus v1 equals to m2 v2 minus u2. Okay, let me call this equation 4. Okay, equation 4, and this comes from equation 1. Okay, now if you do 4 divided by 3, actually 3 divided by 4, what you have is u1 plus v1 equals to v2 plus u2, which is exactly this relationship for elastic collision that we would like to prove. Okay, so the details of how to do all of this, please try to figure it out by yourself, but it is quite straightforward. Okay, again, I would like to emphasize that this relationship can only be applied to elastic collision, but not in elastic collision. Okay, now I give this to you as homework too, to determine whether this situation where you have a truck and a car colliding with each other, is this an elastic collision or inelastic collision. Okay, that is your homework too. Then this is about nuclear reaction. So at the beginning, if you have a big nucleus, and then after that the big nucleus is broken down into a smaller nucleus and alpha particle, okay, how is what is the ratio of the kinetic energy of this guy to the kinetic energy of this guy? So one thing that you may need to know is that you can think of this as a collision as well, but the reverse collision. Okay, why is it reverse collision? Because if you reverse the time, if you reverse out the time, you see that the dot nucleus here will, instead of moving to the left, it will move to the right, and the alpha particle, instead of moving to the right, it will move to the left, and then it will collide each other and give you this parent nucleus. So that means you can use conservation of momentum here as well. How to do it? I'll just give you a rough idea. So you start with p before as a vector is equals to sigma p before equals to sigma p after. Okay, so what is p before? You can see that because the parent nucleus does not move at all, so p before would be equal to vector 0. Now what is p after? P after is equals to p daughter plus p alpha. Okay, so this is written in terms of vector. This sigma sign means that you always add two vectors together. Okay, but because this is the motion in one dimension, so you, instead of writing it as a vector, you can write it down in terms of scalar, but use notation plus or minus to determine the sign. Now if I say that going to the right is plus, going to the left is minus, then what we have here is just 0 equals to minus p daughter plus p alpha. Okay, this is in terms of the magnitude of the momentum. All right. Okay, so from here that means m daughter v daughter will be equals to m alpha v alpha. Okay, and so from here you can find the ratio between vd and v alpha. Okay, you can find vd over v alpha equals to m alpha over md. But the question asks you to find the ratio of the kinetic energy, right? So I will continue the calculation here. So we want to find ek of alpha over ek of daughter. Okay, so that would mean 1/2 of m alpha v alpha square over 1/2 of m daughter v daughter square. So that would be m alpha over m daughter v alpha square over v daughter square. But because now we know that v daughter over v alpha is m alpha over m daughter, so we can have finally what we have is v alpha over v daughter. Okay, so that is the result. The ratio between kinetic energy of the alpha particle and the thorium nucleus, which is the daughter nucleus, is equals to the velocity of v alpha over the velocity of the speed of v alpha over the speed of daughter, the thorium nucleus, after it breaks down. Okay, just that. Okay, I hope it is clear. And then this question is about the bullet of mass m with speed v0 fire into a wooden block with mass m. The bullet is stuck in the wooden block and the block swings up to the height h. Show that h equals to this. So in order to calculate this, first of all you need to realize that this is just a kind of collision where the bullet is just stuck with the block. The bullet of mass m just stuck with the block of mass big M. Okay, so first of all you write down the equation for conservation of momentum before. Okay, so what we have is p before equals to p after. Okay, so what is p before? P before is just the mass of the bullet multiplied by the velocity of the bullet, okay, initially, and that would be equals to what happened afterwards, which is that both the bullet and the block is moving together with some other velocity, let's call it v. So that would be m plus m, and then just v. Okay, Now in terms of, because these two things must point in the same direction, so we can just throw away the vector sign, and what we have is just v0 equals to m plus big M v. Okay, so that is equation 1. Now what is this v? This v is the velocity of the bullet and the block right after it hit the block, and then so that means what happened is that if you have this, so this is the block with the bullet inside, and then so this is right after it hits, and the velocity of this system right after it hits is this v. Okay, so what we need to do next is to think of the system as starting with this v, and then it goes up here. Okay, it moves up here, so that what happened is it changed this kinetic energy into this potential energy m, small m plus big M, G and H. Okay, so that leads us to the second equation, which is m plus m v, so 1/2 of that square equals to m plus m g h. Okay, so this is the kinetic energy right after right after the bullet hits, and this one is the potential energy of the system. Okay, so and we will say that this is equation 2. So solving these two equations, and you get this answer. Okay, I'll let you try that by yourself. So next, let us talk about collision in 2 dimensions with our external force. So this is similar to collision in 1 dimension with our external force, but in this case you need to think about momentum in 2 direction. So in the x direction or and in the y direction, the momentum in both directions has to be conserved. So that means in the x direction, this px0 means the momentum in the x direction at time t equals to 0. I says that this is in the x direction must be equals to pxt, or the momentum in the x direction at time t, and I again say that the direction is in the x direction, and that is also true for the y direction. Py at time t0 must be equals to py at any time t. Okay, so let's look at this. Sorry about that. Let's look at this question. 2 particles are moving with velocity as shown in the diagram. Determine the velocity of both particles after the collision, assuming that the collision is, well, I did a wrong thing here. It has to be inelastic. Okay. Well, maybe inelastic is not the right word. Assuming that the 2 particles stick together after the collision. Okay, so yeah, let's change the question to be like that. Determine the velocity of both particles after the collision. Assuming that the two particles stick together after the collision. Okay, so what does that mean? It means that after the collision, the two particles just move with the same velocity. Okay. Okay. So the two particles will move with the same velocity after the collision. So how do we find the velocity of both particles then? We'll do it this way. First of all, we write down the conservation of momentum, and in this case it's just the collision in two dimensions. So we need to write down two equations for momentum in x direction and momentum in y direction. First of all, the momentum in the x direction, so sigma px before must be equal to sigma px after. Okay, so what is the total momentum in the x direction before the collision? As you can see, before the collision, only this mass has momentum in the x direction, and this mass has no momentum in the x direction at all. So before the collision, what we have is just 0.4 multiplied by 3. That is the total momentum of the system before it collides with each other. Now after the collision, because the two particles move with the same velocity, so that means the total momentum would be 0.4 multiplied by, let's say, Vx plus 0.6 multiplied by Vx, and so that would mean 1.2 must be equal to Vx. Okay, so that is the first equation, and actually yeah, that's the first equation. Now the second equation would be sum of py before must be equal to sum of py after. Okay, so what is the total momentum in the y direction before the collision? So you can see that only this mass has the momentum in the y direction before the collision. So we have 0.6 multiplied by 2 must be equals to 0.4 Vy plus 0.6 Vy. Again, we have this expression due to the fact that after the collision both masses have the same velocity. Okay, so that means this has this is 1.2 and this is Vy. Okay, this is the second equation. Now the question asks you to determine the velocity of both particles. So because both particles have the same velocity, now we can say that after the collision, the velocity of both mass in the y direction is 1.2 meter per second. 1.2 meter per second, and the velocity in the x direction of both particles will become 1.2 meter per second as well, and that is the answer to these questions. Okay, now before we end our lecture this time, we would like to talk about impulse and momentum. So what is impulse and what is momentum? Impulse is defined as the integral of the force F with the time dt from time t equals to t1 to time t equals to t2. So as because this integral is the integral of a scalar quantity dt and a vector quantity f, which is the force. So this guy is just force. So vector multiplied with scalar will give you a vector. So impulse is the vector quantity. Okay, so impulse, this is a vector quantity. So you need both the magnitude and the direction when you talk about impulse. Now, why do we care about this integral at all? Because if you think about Newton's second law, integral of f dt from t1 to t2 must be equals to the difference in the momentum from t2 to t1. Sorry, from t1 to t2. And why is that? So Newton's second law says that the total f must be equals to dp by dt, right? So if you instead of if you change this into integral of sigma f dt, that would be integral of dp, which is just delta p basically, t1 t2 t1 t2. So that would be p at t2 minus p at t1. Okay. So actually, if you want this equation to be precisely correct, then you need a sigma sign here as well, right? So this just means that impulse, if you calculate the impulse, what you have is the impulse would be the same as the change in the momentum of the system. Okay, impulse is just equals to the change in the momentum of the system. So if you want to see how the momentum of the system change, you can just calculate the impulse. Now, if you plot a graph between f and t, f is the force and t is the time, because impulse is defined as the integral. So in terms of the graph, just like what we did before, the integration means the area under the curve. Okay, so if you plot the graph between f and t and then you want to find impulse, that is just equals to this area under the curve. Alright, okay, so now let's look at this question. A tennis ball with mass m equals to 60 grams is moving at velocity u equals to 30 meters per second. After it is hit with a racket, the velocity becomes v equals to 30 meters per second in the opposite direction. Okay, so what happened is just like in this picture. The ball is moving in from left to right with velocity 30 meters per second to the right, and then the racket hit it so that it moved back from the right to the left with this velocity again 30 meters per second. Okay, now we want to find we plot a graph between the force and the time, and we see that it looked like this. The question asks you to find the maximum force F max at this point. So what is the value of this F max? That is the question. Okay, so how do we find this? Well, we must use the fact that integral of f dot dt is equals to so in this case just the magnitude of f, that will be equals to the area under the curve, and also that must be equals to the magnitude of let's say the magnitude of delta p, okay, the change in the momentum of the system. Okay, so first let's try to calculate the area of this curve, area under the curve. You can see that this curve, the area under this curve is just the area of this triangle. Okay, and the formula for the area of the triangle is just equals to 1/2 multiplied by the base, the length of the base, which in this case is 5 millisecond. Okay, and then multiply by the height of this triangle, and the height is just f max. Okay, so you have f max, so that would be equal to 2.5 f max. All right, now so that is the area under the curve. So in order to find f max, you need to find delta p, the magnitude of delta p. Now you can see that the momentum of okay, so delta p is just well, so this is just p2 minus p1. Okay, so what is p2? P2 well, before we do that, we need to specify the sign. So if you go to the right, that is a plus sign. If you go to the left, that is the minus sign. So in this case, our P2 is equals to minus the mass of the okay, so let me do it step by step. Mass and V2. Okay, so the mass of the ball is 60 grams multiplied by V2, which is 30, but because it is going to the left, this is minus 30, and that would be equals to minus 18 sorry, 1.8 thousand. Okay, gram, okay, meter per second. And then P1 is equals to mv1, and that is equals to again 60 multiplied by 30, that will be a plus 1800 gram meter per second. Okay, so from this P2 minus P1 would be equals to minus 1800 minus 1800, that is equals to minus 3600 gram meter per second. Okay, so that is delta P, P2 minus P1. Now what you want is just the magnitude of P2 minus P1, so it's just 3600. Okay, so in the end what you have is area equals to the magnitude of delta P, and so that would be 2.5 F max equals to 360, and so F max is equals to 360, sorry, the 3600 over 2.5, that is whatever. Okay, and the unit has to be in newtons, so you need to be careful because you need to change the unit properly. In this question, the mass is given in grams, the velocity is given in meter per second. Okay, so yeah, you need to be careful. Anyway, so that is how you find F max in these questions, and that should be it for today's lecture. Thank you very much, everyone. See you again next time.